Welcome to Sleepy Science Odyssey. Tonight, Earth mysteries, the unsolved puzzles of our planet, from the unexplained mechanisms driving continental drift to the origins of Earth's magnetic field, from the causes of ice ages to the mysteries of deep ocean trenches, from the formation of the moon to the chemistry that sparked life, from anomalies in gravity to patterns in mass extinctions, from the nature of Earth's core to the sources of earthquakes. We'll explore what science knows, what remains uncertain, and why understanding these mysteries matters for understanding the planet we inhabit. If you're new here, this channel is for people who need something to think about before they can stop thinking. Real Earth science, no exaggeration, just quiet facts in the dark. Let's begin. Earth's magnetic field reverses polarity irregularly, and we don't fully understand why or when the next reversal will occur. The Earth's magnetic field extends thousands of kilometers into space, shielding the planet from solar wind and cosmic radiation while providing the compass navigation that has guided travelers for centuries. Yet this field exhibits strange behaviors, including irregular reversals, where north and south magnetic poles swap positions. A phenomenon recorded in rocks, but not fully explained by theory, representing one of Earth's fundamental mysteries. The magnetic field originates in Earth's outer core, approximately 3,000 kilometers below the surface, where liquid iron moves in convective patterns driven by heat from the solid inner core and residual heat from Earth's formation. This motion of electrically conducting fluid generates electric currents through a process called the geodynamo, and these currents produce the magnetic field. The details of how this self-sustaining dynamo operates remain incompletely understood despite sophisticated computer simulations. Magnetic field reversals have occurred throughout Earth's history, recorded in volcanic rocks and seafloor sediments. When lava cools, magnetic minerals align with the ambient magnetic field, freezing a record of the field direction at that time. By studying rocks of different ages worldwide, scientists have reconstructed the reversal history, extending back hundreds of millions of years. The pattern is irregular. Reversals occur at unpredictable intervals, ranging from thousands to millions of years, with the average being approximately 200,000 to 300,000 years. The most recent reversal, called the Brunnsmatt-Yama reversal, occurred approximately 780,000 years ago. This means Earth is in the Brun's normal polarity epoch, normal referring to the current configuration where magnetic north is near geographic north. Before the Brunnsmatt-Yama reversal was the Matt-Yama reversed epoch, extending to approximately 2.6 million years ago, when magnetic north was near geographic south. The timing of these epochs varies, with some lasting millions of years and others only tens of thousands. The process of reversal itself remains mysterious. The transition doesn't occur instantaneously, but takes approximately 1,000 to 10,000 years to complete. During this transition, the field weakens substantially, dropping to perhaps 10 to 20% of normal strength, and becomes complex with multiple poles appearing at various locations. The weakened field during reversals would allow more cosmic radiation to reach Earth's surface, potentially affecting climate, atmospheric chemistry, and evolutionary processes, though evidence for such effects is debated. The current magnetic field strength has declined approximately 10 to 15% over the past 200 years, measured through both direct observations since the 1600s and indirect proxies including pottery, bricks, and other fired materials that record field strength when heated. Some researchers interpret this decline as potentially indicating an impending reversal, though others note that field strength fluctuates on various timescales, and the decline might simply be part of normal variation without presaging a reversal. The South Atlantic anomaly represents a region where the magnetic field is significantly weaker than surrounding areas, stretching from South America to southern Africa. Satellites passing through this region experience higher radiation doses and increased rates of electronic malfunctions. The anomaly reflects complex field geometry with localized weakening, possibly related to structures deep in the core. Some researchers suggest the anomaly might be an early manifestation of reversal initiation, though this interpretation is speculative. Paleomagnetic studies reveal that reversal frequency has varied dramatically over Earth's history. During the Cretaceous normal superchron from approximately 83 to 121 million years ago, no reversals occurred for nearly 40 million years, an extraordinarily stable period. Conversely, during some periods, reversals occurred every 10,000 to 50,000 years. The causes of these variations in reversal frequency remain unclear, though they may relate to changes in core dynamics, lower mantle structure, or heat flow patterns. The possibility of excursions, brief periods when the field weakens and becomes complex without completing a full reversal, adds additional complexity. The Lachamp excursion approximately 41,000 years ago saw the field weaken and the dipole tilt significantly for several hundred years before recovering to normal polarity. Such excursions might represent failed reversals, where the dynamo begins transitioning but returns to the original state. Evidence for excursions comes from sediment cores, volcanic rocks, and cosmogenic isotopes produced when cosmic rays strike the atmosphere. The biological impacts of reversals remain uncertain but potentially significant. The magnetic field shields Earth from solar wind and cosmic radiation, so weakening during reversals could increase surface radiation exposure. Some researchers have proposed links between reversals and extinction events, though the evidence is inconclusive. The Lachamp excursion coincided with megafaunal extinctions in Australia and possible climatic changes, but establishing causation is difficult given numerous confounding factors. Technological impacts of a reversal or major excursion could be substantial in our technologically dependent civilization. Satellites, power grids, communication systems, and navigation infrastructure could all be affected by increased radiation, geomagnetic storms, and compass failure during transition periods. The gradual nature of reversals, occurring over thousands of years, would allow adaptation, but the weakened field during transition could create centuries of heightened vulnerability to solar storms and cosmic ray events. The fact that reversals occur at all reveals that Earth's magnetic field is not a simple, stable dipole, but a dynamic system capable of complex reorganization. Computer simulations of the geodynamo can produce reversals, but predicting when they'll occur or understanding what triggers them remains beyond current capabilities. The simulations reveal that reversals can emerge spontaneously from turbulent core dynamics without requiring external triggers, though external factors like mantle heterogeneity or core mantle boundary topography might influence reversal frequency. The asymmetry of Earth's magnetic field, stronger in some regions, weaker in others, reflects complex flow patterns in the outer core. The field is not a perfect dipole aligned with Earth's rotation axis, but includes quadrupole, octupole, and higher-order components. The dominant dipole component is tilted approximately 11 degrees from the rotation axis and offset from Earth's center. These complexities arise from the three-dimensional structure of core convection, which varies spatially and temporally in ways we can only partially observe through surface magnetic measurements. The connection between reversals and other Earth systems remains an active research area. Some studies suggest correlations between reversal frequency and mantle plume activity, plate tectonic reorganizations, or ice age cycles, but establishing causation is challenging. The core and mantle are coupled through thermal and mechanical interactions at the core-mantle boundary, so changes in one system can potentially influence the other. However, the mechanisms and magnitudes of such interactions remain poorly quantified. The search for patterns in the reversal record continues. Some researchers have proposed periodicities, regular or quasi-regular timing between reversals, but statistical analyses yield contradictory results, with some finding evidence for periodicities of approximately 15 million or 30 million years, while others find the record consistent with a random Poisson process. The irregularity might simply reflect the chaotic nature of turbulent fluid dynamics in the core, where deterministic equations produce unpredictable long-term behavior. The core-mantle boundary, where the liquid outer core meets the solid lower mantle approximately 2,900 kilometers below the surface, plays a crucial but incompletely understood role in geodynamo processes. This boundary is not smooth, but features topographic variations of several kilometers and large low-shear velocity provinces, or LLSVPs, massive regions where seismic wave speeds are anomalously low. These structures, located beneath Africa and the Pacific, may represent chemically distinct material or exceptionally hot mantle, and they influence the overlying core flow patterns. The coupling between core dynamics and mantle structure occurs through multiple mechanisms. Thermal coupling involves heat transfer from the core to the mantle, with variations in mantle structure creating heterogeneous heat extraction patterns that affect core convection. Topographic coupling occurs when core flow must navigate the irregular core-mantle boundary topography. Electromagnetic coupling can occur if the lower mantle has sufficient electrical conductivity. These couplings create complex interactions where mantle evolution affects the geodynamo, and vice versa. The chemical composition of the outer core remains incompletely constrained despite being crucial for understanding dynamo processes. The core is primarily iron with approximately 5 to 10% nickel, but seismic data indicate the presence of light elements reducing density below pure iron values. Proposed light elements include sulfur, silicon, oxygen, carbon, and hydrogen in various combinations. Different light element contents affect the core's thermal and compositional convection, influencing the geodynamo. Experiments at core pressures and temperatures are challenging, leaving uncertainties about which elements are present and in what proportions. The power source driving core convection has evolved over Earth's history. Initially, rapid cooling from Earth's formation drove vigorous convection. As the planet cooled, the inner core began crystallizing, releasing latent heat and light elements that drive compositional convection. Lighter material rises while denser material sinks. Radioactive decay of potassium-40 and possibly uranium and thorium in the core may contribute additional heat, though the concentration of these elements in the core is debated. The balance of these energy sources has changed over time, potentially affecting reversal frequency. The paleointensity of the magnetic field, its strength in the past, can be estimated from rocks and archaeological materials. Single crystals of magnetic minerals in rocks record not only field direction, but also intensity through their magnetization strength. Archaeological materials, including fired pottery, hearths, and bricks, provide historical records of field strength. These records reveal that field strength has varied substantially over the past several thousand years, with periods of high strength exceeding current values and periods of low strength approaching half current values. The westward drift of the magnetic field, the observation that field features, including the South Atlantic anomaly, move westward at approximately 0.2 degrees per year, has been documented for centuries. This drift reflects the rotation of fluid in the outer core relative to the mantle. The drift rate varies spatially and temporally, with some features moving faster or slower than average, and some even drifting eastward. Understanding these motions provides constraints on core flow patterns and their relationship to field generation. The Moon's origin remains debated despite the giant impact hypothesis being widely accepted. The Moon dominates Earth's night sky, influences ocean tides, and has stabilized Earth's axial tilt for billions of years. Yet fundamental questions about how it formed remain incompletely answered. The giant impact hypothesis, proposing that the Moon formed from debris ejected when a Mars-sized body struck Earth approximately 4.5 billion years ago, has become the leading explanation, but significant mysteries and inconsistencies persist. The giant impact hypothesis, also called the Theia impact hypothesis, after the proposed impactor named for a Greek titan, emerged in the 1970s to explain multiple puzzles about the Moon. The hypothesis proposes that early in Earth's history, a planetary embryo, perhaps 10% of Earth's mass, struck at an oblique angle, vaporizing much of the impactor and ejecting enormous amounts of material into orbit. This debris, heated to thousands of kelvins and partially vaporized, coalesced to form the Moon over timescales of months to years. The hypothesis successfully explains several key observations. The Moon's bulk composition is similar to Earth's mantle, but depleted in volatiles, elements and compounds with low boiling points, consistent with formation from hot, vaporized material where volatiles escape to space. The Moon is depleted in iron compared to Earth, consistent with formation primarily from mantle material rather than core material, which would have remained in Earth during the impact. The Earth-Moon system has high angular momentum, consistent with a large off-center impact imparting substantial rotational energy. However, significant problems challenge the simple giant impact model. The Moon's isotopic composition is nearly identical to Earth's for multiple elements including oxygen, chromium, and tungsten, whereas Theia should have had a different composition, reflecting a different formation location in the solar nebula. Computer simulations of the impact typically produce moons with compositions dominated by Theia material rather than Earth material, contradicting the isotopic similarity. Various solutions have been proposed. Perhaps Theia happened to have the same composition as Earth, or perhaps the impact vaporized and mixed the materials thoroughly, but each has limitations. The lunar rock samples returned by Apollo missions revealed that Moon rocks are extremely dry, containing less than 1 part per million water in most minerals, compared to hundreds of parts per million in Earth's mantle. This depletion extends to other volatiles including zinc, potassium, and sodium, supporting the hypothesis that the Moon formed from hot material. However, Recent discoveries of water in lunar volcanic glasses and in permanently shadowed polar craters complicate this picture, suggesting some water survived the formation process or was delivered later. The Moon's size relative to Earth is larger than any other planet-moon system in the solar system, except Pluto-Charon, which formed through different mechanisms. The Earth-Moon mass ratio of approximately 81:1 seems to require a specific impact scenario. Too small an impactor wouldn't eject enough material to form the Moon. Too large an impactor would destroy Earth or create a very different system. The narrow range of viable impact parameters raises questions about how likely such an event was and whether Earth-Moon systems are common or rare around other stars. The timing of the Moon-forming impact is constrained by radiometric dating of lunar samples, indicating Moon formation approximately 4.51 billion years ago, within approximately 100 million years of solar system formation. This timing comes from uranium-lead dating of zircon crystals in lunar rocks and from hafnium-tungsten isotope systematics reflecting core formation timing. The early formation means the Moon witnessed the late heavy bombardment and has preserved a record of early solar system dynamics in its cratered surface. Alternative Moon formation hypotheses have been proposed but face greater challenges than the giant impact model. The fission hypothesis, proposed by George Darwin in the 19th century, suggested the Moon split from a rapidly rotating Earth, but this requires unrealistically rapid rotation and doesn't explain isotopic similarities or angular momentum distribution. The co-accretion hypothesis proposed that the Moon formed alongside Earth from the same part of the solar nebula, but struggles to explain the Moon's iron depletion. The capture hypothesis suggested Earth gravitationally captured a preformed Moon, but capturing into a nearly circular orbit is dynamically implausible without a mechanism for energy dissipation. Variations of the giant impact hypothesis attempt to resolve the isotopic similarity problem. The multiple impact hypothesis proposes that several smaller impacts created disk material that mixed between impacts, homogenizing isotopic compositions. The fast-spinning Earth hypothesis proposes that the impact left Earth rotating with a 2-hour day, creating a rotationally supported disk where material from Earth and Theia mixed before coalescing into the Moon. The synestia hypothesis proposes that the impact created a donut-shaped cloud of vaporized rock called a synestia, within which the Moon formed and exchanged material with Earth until isotopic equilibration occurred. The Moon's influence on Earth has been profound. Tidal interactions transfer angular momentum from Earth's rotation to the Moon's orbit, gradually slowing Earth's rotation and increasing the Moon's orbital distance. When the Moon formed, it was perhaps 20 times closer than today, and Earth's day was perhaps 5 to 6 hours long. Tidal dissipation has lengthened the day to 24 hours and moved the Moon to its current distance of approximately 380,000 kilometers. This process continues today at approximately 3.8 centimeters per year. The stabilization of Earth's axial tilt by the Moon has important implications for climate stability. Without the Moon, gravitational perturbations from other planets would cause large variations in Earth's axial tilt on timescales of millions of years, potentially causing extreme climate swings. The Moon stabilizes the tilt at approximately 23.5 degrees, still varying by about 1 degree on 41,000-year cycles, but preventing the chaotic variations that might occur otherwise. This stability may have been important for the evolution of complex life by maintaining relatively stable climate patterns. The origin of the Moon connects to broader questions about planet formation and the frequency of giant impacts in planetary systems. Computer simulations of terrestrial planet formation reveal that giant impacts are common in the final stages, with planets undergoing multiple collisions as they sweep up remaining planetesimals and planetary embryos. Earth may have experienced several large impacts, with the Moon-forming impact being the last major collision. Understanding how common such events are helps assess whether Earth-like planets with large moons are typical or unusual. The search for exomoons, moons orbiting planets around other stars, has begun but remains technically challenging given the small signals moons produce. Detecting moons the size of Earth's moon around Earth-sized planets at interstellar distances pushes the limits of current technology. Future telescopes may detect exomoons through transit timing variations or direct imaging, revealing whether large moons are common and providing comparative context for understanding the Earth-Moon system. The lunar interior remains incompletely understood despite seismic data from Apollo seismometers. The Moon has a small iron core approximately 350 kilometers in radius, much smaller proportionally than Earth's core, consistent with iron depletion in Moon-forming material. The mantle is rich in magnesium and iron silicates, and the crust is enriched in aluminum and calcium, reflecting magma ocean differentiation early in lunar history. However, the presence of a partially molten asthenosphere and the details of interior structure remain uncertain. The asymmetry between the Moon's near and far sides represents another mystery. The near side has extensive maria, dark basaltic plains formed from ancient lava flows, while the far side has far fewer maria and a thicker crust. The South Pole-Aitken Basin on the far side is one of the largest impact basins in the solar system, yet it didn't fill with lava like near-side basins. Proposed explanations for the near-far asymmetry include variations in crustal thickness affecting magma ascent, differences in heat production from radioactive elements, or tidal heating preferentially affecting the near side. The composition of the lunar crust varies between the terry, bright highlands composed of anorthosite, a rock rich in calcium-aluminum silicate feldspar, and the maria. The highlands represent the primordial crust formed when plagioclase crystals floated to the top of the lunar magma ocean, while the maria are younger basaltic flows that filled impact basins. This dichotomy records the Moon's thermal evolution from a molten state through cooling and solidification. But questions remain about the duration of the magma ocean, the depths from which mare basalts originated, and the timeline of volcanic activity. The KREP terrain, a region enriched in potassium, K, rare earth elements, REE, and phosphorus, P, represents the last magma ocean liquid to crystallize, concentrated in incompatible elements. This material is exposed in the Procellarum KREP terrain on the lunar near side, and is associated with elevated radioactive element concentrations that have provided heat for prolonged volcanic activity. The connection between KREP distribution and near-far asymmetry remains an active research question. The late heavy bombardment hypothesis proposes that the inner solar system experienced intense bombardment approximately 4.1 to 3.8 billion years ago, approximately 600 million years after solar system formation. Evidence comes primarily from lunar samples showing clustering of impact melt ages around 3.9 billion years ago. The hypothesis suggests a dynamical event possibly migration of giant planets, destabilized the asteroid belt and scattered planetesimals throughout the inner solar system. However, the reality and timing of the LHB are debated, with some researchers arguing that the apparent age clustering reflects sampling bias or multiple impacts into already melted material. The preservation of ancient surfaces on the Moon provides a window into early solar system bombardment history unavailable on Earth, where plate tectonics and erosion have destroyed ancient rocks. The lunar crater record, extending back over 4 billion years, constrains impact rates and projectile populations. However, interpreting this record requires understanding how impact crater production and erasure rates have varied over time, secondary cratering from debris ejected by large impacts, and the relationship between crater counts and absolute ages. The origin and evolution of the lunar magnetic field represents another mystery. Lunar rocks carry remnant magnetization, indicating the presence of a magnetic field when they crystallized. Yet the Moon currently has no global magnetic field. The small size of the lunar core and rapid cooling should have precluded a long-lived dynamo. Yet paleomagnetic evidence suggests the field persisted from approximately 4.2 to 3.5 billion years ago, and may have been as strong as Earth's field at its peak. Proposed mechanisms for generating this field include a core dynamo powered by precession, mechanical stirring from impacts, or other processes, but no consensus exists. Ice ages occur at regular intervals controlled by orbital variations, but the mechanisms linking orbital changes to glaciation remain incompletely understood. The Earth has experienced multiple ice ages over the past 2.6 million years, with massive ice sheets covering substantial portions of North America, Europe, and Asia during glacial maxima, interspersed with warmer interglacial periods like the present. The timing of these glacial-interglacial cycles correlates remarkably with variations in Earth's orbit and axial tilt, the Milankovitch cycles. Yet how small changes in solar radiation distribution trigger massive ice sheet growth remains an active area of research. The Milankovitch cycles are named for Serbian scientist Milutin Milankovic, who in the early 20th century calculated how orbital variations affect solar radiation distribution across Earth's surface. 3 main cycles operate on different timescales. Eccentricity, the shape of Earth's orbit varying from nearly circular to slightly elliptical on approximately 100,000-year cycles. Obliquity, Earth's axial tilt, varying between approximately 22 and 24.5 degrees on approximately 41,000-year cycles. And precession, the direction Earth's axis points varying on approximately 21,000-year cycles. These orbital variations change the seasonal and latitudinal distribution of solar radiation reaching Earth, but have minimal effect on total annual solar energy. Eccentricity changes total annual radiation by less than 0.2%. Obliquity changes the contrast between seasons. Higher tilt means warmer summers and colder winters, and affects how much radiation reaches polar regions. Precession determines which season occurs at perihelion, Earth's closest approach to the Sun, affecting northern versus southern hemisphere seasonal intensity. The 100,000-year glacial cycle dominates the climate record of the past 800,000 years, with major glaciations recurring at roughly this interval. This timing matches the eccentricity cycle, but the mechanism is puzzling because eccentricity has the smallest direct radiative forcing. The 100,000-year problem refers to the mystery of why climate responds so strongly to weak eccentricity forcing. Proposed explanations include eccentricity modulating the precession cycle's amplitude, ice sheet dynamics amplifying small forcings, or carbon dioxide feedbacks dominating the response. The marine sediment record preserves evidence of glacial cycles through oxygen isotope ratios in foraminifera shells. Water molecules containing oxygen-16 evaporate more readily than those with oxygen-18. So when ice sheets grow by accumulating snow from evaporated ocean water, they preferentially lock up oxygen-16, leaving the ocean enriched in oxygen-18. Foraminifera incorporate oxygen from seawater into their shells, recording the isotopic ratio at the time they grew. The resulting oxygen isotope curve shows clear approximately 100,000-year cycles over the past million years. Earlier glacial cycles, from approximately 2.6 to 1 million years ago, had different characteristics with dominant periods of approximately 41,000 years matching the obliquity cycle. The mid-Pleistocene transition approximately 900,000 to 1,200,000 years ago marked a shift from 41,000-year to 100,000-year cycles without clear changes in orbital forcing. What caused this transition remains mysterious, though hypotheses include gradual cooling, allowing larger ice sheets to develop, changes in ice sheet basal conditions, or carbon dioxide declining to levels where orbital variations can trigger large glaciations. Ice core records from Antarctica and Greenland provide direct evidence of past climate extending back approximately 800,000 years in Antarctic cores. These cores reveal tight coupling between temperature and carbon dioxide concentrations, with CO2 ranging from approximately 180 parts per million during glacial maxima to approximately 280 parts per million during interglacials. The CO2 variations amplify orbital forcing. When orbital configurations favor cooling, carbon dioxide declines, reinforcing cooling through reduced greenhouse effect, creating positive feedback. The mechanisms controlling glacial-interglacial CO2 variations remain incompletely understood despite decades of research. The ocean contains approximately 60 times more carbon than the atmosphere, so small changes in ocean carbon storage significantly affect atmospheric CO2. Proposed mechanisms include temperature-dependent CO2 solubility in seawater, biological carbon pump efficiency changes, ocean circulation changes affecting deep water formation, and sea ice extent affecting air-sea gas exchange. Multiple mechanisms likely operate simultaneously, but their relative importance and interactions remain debated. The termination of glacial periods, the transitions from glacial maxima to interglacial warmth, occur relatively rapidly compared to the gradual glacial inception and growth. Terminations take approximately 5 to 10,000 years, while glacial inception can take 20 to 40,000 years. This asymmetry might reflect positive feedbacks during deglaciation, including ice albedo feedback. As ice melts, darker land or ocean absorbs more solar radiation, accelerating melting, and carbon dioxide release from warming oceans amplifying warming. The last glacial maximum, approximately 20,000 to 26,000 years ago, represents the most recent major glaciation. Ice sheets covered Canada and the northern United States, Scandinavia, and parts of Russia, with ice thickness exceeding 2 kilometers in places. Sea level was approximately 120 meters lower than present because ocean water was locked in ice sheets. Global average temperature was approximately 4 to 7 degrees Celsius cooler than the pre-industrial Holocene. The deglaciation from the LGM to the Holocene interglacial took approximately 15,000 years, with rapid transitions and regional variations. Abrupt climate changes punctuated the last glacial period, demonstrating that climate can shift dramatically on decadal timescales. Danskardischer events, rapid warmings of approximately 8 to 16 degrees Celsius in Greenland, occurring over decades, happened approximately 25 times during the last glacial period. Heinrich events, massive iceberg discharges from the Laurentide ice sheet carrying sediment into the North Atlantic, occurred approximately every 7 to 10,000 years, causing abrupt cooling. These events reveal climate system instability during glacial periods, possibly related to ice sheet dynamics or ocean circulation changes. The Younger Dryas event, approximately 12,800 to 11,600 years ago, represented a return to near-glacial conditions, interrupting the deglaciation. This millennium-long cooling affected the northern hemisphere particularly strongly, with Greenland temperatures dropping approximately 15 degrees Celsius. The cause is attributed to freshwater from melting ice sheets disrupting the Atlantic meridional overturning circulation. The ocean current system, including the Gulf Stream, reducing heat transport to high northern latitudes. The event demonstrates climate sensitivity to ocean circulation changes. Glacial cycles extend much further back than the Pleistocene ice ages. The late Paleozoic ice age from approximately 360 to 260 million years ago saw extensive glaciation in Gondwana. The Snowball Earth episodes approximately 720 and 635 million years ago may have seen ice extending to tropical latitudes, covering most or all of the planet. These ancient glaciations had different causes than Pleistocene cycles: continental positions affecting ocean circulation, atmospheric composition changes, and possibly variations in solar luminosity or volcanic activity. The role of ice sheet dynamics in glacial cycles remains an active research area. Ice sheets don't respond passively to orbital forcing, but have internal dynamics affecting their growth and decay. Basal conditions, whether ice rests on bedrock or deformable sediments, affect flow rates. Calving of icebergs and submarine melting at marine margins affect stability. Ice streams, regions of rapid ice flow, can drain ice sheet interiors. These dynamics create thresholds and nonlinearities where small forcings can trigger large responses, or where large forcings might have minimal effects depending on ice sheet state. The future of glacial cycles in the context of anthropogenic climate change raises interesting questions. Human greenhouse gas emissions have elevated atmospheric CO2 to levels unprecedented in at least the past 800,000 years, exceeding 400 parts per million compared to the natural interglacial maximum of approximately 280 parts per million. This elevation might prevent the next glacial inception, expected in approximately 50,000 years based on orbital cycles. Some researchers suggest we've initiated a super-interglacial that could persist for hundreds of thousands of years, fundamentally altering the glacial cycle pattern. The role of dust and aerosols in glacial cycles represents another layer of complexity. Ice core records show that atmospheric dust concentrations were much higher during glacial periods than interglacials, with dust levels increasing by factors of 10 to 25. This dust, primarily from expanded deserts and exposed continental shelves, affected climate by scattering solar radiation, seeding clouds, and fertilizing oceans with iron that stimulated phytoplankton growth and carbon uptake. The interplay between ice sheets, dust sources, ocean productivity, and atmospheric composition creates complex feedbacks. The extent of ice sheets during glacial maxima is reconstructed from multiple lines of evidence. Moraines, piles of rocks and sediment deposited at ice sheet margins, mark maximum extents. Glacial erratics, boulders transported far from their sources, indicate ice coverage. Glacial striations on bedrock show ice flow directions. Marine sediment cores containing ice-rafted debris reveal iceberg distributions. These observations constrain ice sheet reconstructions, but uncertainties remain about ice thickness distributions, flow dynamics, and temporal evolution. The isostatic adjustment of land following ice sheet removal continues today, thousands of years after deglaciation. During glaciation, ice sheet weight depressed the crust into the mantle. After ice melted, the crust rebounds upward through viscous flow of mantle material, a process called glacial isostatic adjustment, or GIA. Scandinavia continues rising at rates up to 1 centimeter per year, and Hudson Bay is rising nearly as fast. This ongoing adjustment affects relative sea level, gravitational fields, and Earth's rotation rate. Understanding GIA is essential for interpreting geodetic measurements and assessing future sea level changes. The connection between ice ages and the evolution of human ancestors has been explored extensively. The Pleistocene glacial cycles coincided with critical periods in hominin evolution, including the emergence of Homo sapiens approximately 300,000 years ago. Some researchers propose that climate variability during this period drove selection for cognitive flexibility, social cooperation, and technological innovation that characterize modern humans. However, linking specific evolutionary changes to climate shifts is challenging given the multiple confounding factors. The refugia where organisms survived glacial periods, areas that remained habitable while surrounding regions were covered by ice or rendered uninhabitable, have been identified through phylogeographic analyses combining genetic data with paleoclimate reconstructions. During glacial maxima, many species contracted to southern refugia, while during interglacials they expanded northward. These range shifts left genetic signatures in population structures that can be detected today, revealing the locations of glacial refugia and the roots of post-glacial expansion. The ocean's role in glacial cycles extends beyond carbon storage to include effects on heat transport, sea ice formation, and water mass properties. Thermohaline circulation, the global ocean conveyor belt driven by density differences from temperature and salinity variations, redistributes heat globally. During glacial periods, changes in freshwater inputs from melting ice, sea ice formation rates, and surface temperature patterns altered circulation pathways. The North Atlantic deep water formation, crucial for modern climate, was weaker or shifted locations during glacial periods, affecting heat transport to high northern latitudes. Earth's inner core may rotate at a different rate than the surface, but observations are ambiguous and controversial. The discovery that Earth's solid inner core might rotate independently of the overlying mantle and surface revolutionized thinking about deep Earth dynamics when first proposed in the 1990s. However, subsequent research has produced conflicting results, with different studies suggesting faster rotation, slower rotation, or no differential rotation, making inner core superrotation one of the most contentious questions in deep Earth science. The inner core is a solid iron-nickel sphere approximately 1,220 kilometers in radius, sitting at Earth's center, surrounded by the liquid outer core, extending to approximately 3,500 kilometers radius. The inner core crystallized from the liquid core as Earth cooled, a process that continues today at a rate of approximately 1 millimeter per year. The solid inner core is distinct from the liquid outer core despite both being primarily iron because the extreme pressure at Earth's center, approximately 330 gigapascals, or over 3 million times atmospheric pressure, raises the melting point above the local temperature. The proposal for inner core superrotation emerged from seismological observations of how seismic waves travel through the inner core. Earthquake waves that pass through the inner core, called PKP waves, referring to the path through the mantle P, outer core K, and inner core P, arrive at seismic stations slightly earlier or later than expected based on standard Earth models. These travel time anomalies can be explained if the inner core has seismic anisotropy, wave speed depending on direction, with fast directions aligned along the rotation axis. If the inner core has seismic anisotropy, and if the pattern of anisotropy is rotating relative to the mantle, then travel times for waves passing through the inner core should change systematically over time. Studies in the 1990s reported such changes, suggesting the inner core rotates approximately 1 degree per year faster than the surface, completing an extra rotation relative to the surface every 360 years. This superrotation was attributed to electromagnetic coupling with the liquid outer core, where the geodynamo preferentially torques the inner core in the direction of Earth's rotation. However, subsequent studies using different earthquake pairs, different time periods, or different analysis methods have produced contradictory results. Some studies confirm superrotation at rates from 0.3 to 1 degree per year. Others find no significant rotation or even slight subrotation, the inner core rotating slower than the surface. Still others suggest the rotation rate has varied over time, with periods of superrotation, periods of subrotation, and periods of no differential rotation. The conflicting results indicate that either the signal is weak and difficult to detect reliably, or the phenomenon is more complex than initially thought. The challenges in detecting inner core rotation are substantial. The signal, small changes in seismic wave travel times over decades, is subtle compared to uncertainties from earthquake location errors, station timing errors, lateral variations in mantle and outer core structure, and inner core heterogeneity. Different studies use different earthquake station pairs, different time periods, different wave phases, and different analysis techniques, potentially explaining some discrepancies. The need to compare seismic data separated by decades, during which instrumentation and analysis methods have changed, adds additional complications. Recent studies using seismic data extending to the 2020s suggest the inner core rotation may have paused or reversed around 2009. Analysis of wave travel times from repeating earthquakes occurring at nearly the same location years apart, revealed systematic changes from the 1970s through approximately 2009, followed by a change in trend suggesting rotation slowed or reversed. If correct, this would indicate the inner core rotation is not steady but variable on decadal timescales, perhaps oscillating back and forth. The physical mechanisms potentially causing inner core rotation or oscillation involve electromagnetic and gravitational coupling between the inner core, outer core, and mantle. The magnetic field generated in the outer core exerts electromagnetic torques on the conducting inner core. Because the magnetic field rotates with the outer core fluid motions, which include both the general westward drift of the field and more complex patterns, the torques on the inner core can vary spatially and temporally. Gravitational torques from mantle heterogeneity, variations in density creating bumps and troughs in the core-mantle boundary, can also affect inner core motion. The geodynamo models that simulate magnetic field generation sometimes predict inner core superrotation as a natural consequence of the magnetic field structure and outer core flow patterns. However, different models produce different predictions depending on assumptions about core properties, including viscosity, magnetic field strength, and inner core boundary conditions. The range of predictions reflects uncertainties in core physics, with parameters poorly constrained by observations. If the inner core does rotate differentially, this has implications for understanding the geodynamo and core dynamics. The relative motion between the solid inner core and liquid outer core creates shear that could affect the flow patterns generating the magnetic field. The inner core might influence the location and stability of magnetic field structures. Changes in inner core rotation rate might correlate with changes in magnetic field strength or reversal frequency, though testing such correlations requires both better constraints on inner core rotation and better understanding of field variations. The seismic anisotropy of the inner core, central to rotation detection efforts, is itself not fully understood. The anisotropy is attributed to preferential alignment of iron crystals, with the crystal structure of iron at inner core conditions having different elastic properties along different crystallographic directions. If crystals align during crystallization or through deformation, the bulk inner core acquires anisotropy. However, the mechanisms causing alignment, whether the alignment is uniform or varies spatially, and how stable the alignment is over time remain subjects of ongoing research. Recent studies have revealed that inner core structure is more complex than a uniformly anisotropic sphere. The innermost inner core, approximately 300 to 400 kilometers radius, may have different anisotropy orientation than the outer inner core, with fast directions perpendicular rather than parallel to the rotation axis. Hemispheric variations exist, with the eastern and western hemispheres of the inner core showing different seismic properties. These complexities suggest the inner core has had a dynamic history with varying crystallization and deformation conditions. Alternative explanations for seismic observations attributed to inner core rotation have been proposed. Temporal changes in outer core structure above the inner core could mimic inner core rotation signals. Changes in mantle structure could affect wave paths. Complexities in inner core heterogeneity that happen to create patterns mimicking rotation could be misinterpreted. Distinguishing these alternatives from true rotation requires careful analysis and ideally multiple independent datasets showing consistent signals. The debate over inner core rotation illustrates the challenges of studying Earth's deep interior. Direct samples are impossible. The inner core is over 5,000 kilometers below the surface, deeper than any drilling could reach. Seismic waves provide the primary constraints, but interpreting them requires assumptions about material properties, structure, and dynamics that have large uncertainties. Different research groups analyzing the same data can reach different conclusions based on different processing choices and assumptions, leading to scientific controversies that can take decades to resolve. The growth rate of the inner core affects its dynamics and Earth's thermal evolution. The inner core grows as heat is extracted from the core, causing the liquid iron alloy to freeze onto the solid inner core boundary. Estimates of the growth rate vary from approximately 0.3 to 1 millimeter per year based on thermal models and age constraints from hafnium-tungsten isotope systematics. This growth releases latent heat that drives core convection, and it preferentially freezes out iron, leaving the outer core enriched in light elements that also drive convection through compositional buoyancy. The mushy zone hypothesis proposes that the inner core boundary is not a sharp interface, but rather a partially molten region containing both solid crystals and liquid. This mushiness could arise from compositional variations, impurities, or temperature gradients, creating a region where melting and freezing occur simultaneously. A mushy zone would affect seismic wave propagation, potentially contributing to observed complexities. However, whether such a zone exists, and if so how thick it is, remains uncertain. The connection between inner core dynamics and the length of day has been proposed based on angular momentum exchange. If the inner core rotates differentially, this transfers angular momentum between the inner core and the rest of the Earth, potentially affecting rotation rate. Observations of decade timescale variations in Earth's rotation rate might correlate with inner core rotation changes. However, other factors including atmosphere-ocean interactions, mantle convection, and post-glacial rebound also affect rotation, making it difficult to isolate inner core contributions. The phase of iron at inner core conditions, whether body-centered cubic, hexagonal close-backed, or some other structure, affects its physical properties including elasticity, thermal conductivity, and viscosity. Laboratory experiments at high pressure and temperature have identified multiple iron phases, but reaching inner core conditions, 360 gigapascals and approximately 6,000 kelvins, remains at the limit of experimental capabilities. Different iron phases have different seismic anisotropies, affecting interpretation of seismic observations and models of inner core structure. The trigger mechanisms for major earthquakes remain imperfectly understood despite advances in understanding fault mechanics. Earthquakes represent the sudden release of accumulated stress on faults, producing seismic waves that can cause devastating ground shaking. While the basic mechanics of earthquakes, elastic rebound as faults slip, are well established, predicting when and where specific earthquakes will occur remains impossible, and even understanding what triggers the transition from stable sliding to dynamic rupture remains an active research area with important unsolved questions. Earthquakes occur when stress accumulated on faults through tectonic plate motion exceeds the frictional strength resisting slip, causing sudden rupture. The elastic rebound theory, proposed by H.F. Reed after the 1906 San Francisco earthquake, describes how rocks deform elastically as stress builds, storing energy like a compressed spring. When strength is exceeded, the fault slips rapidly, releasing the stored energy as seismic waves and heat. The rocks rebound to less deformed configurations, though not to their original states because permanent offset has occurred. The seismic cycle for a given fault segment involves interseismic periods of stress accumulation through steady tectonic loading, coseismic slip during earthquakes releasing accumulated stress, and post-seismic adjustment through continued fault creep, viscoelastic relaxation, and aftershock sequences. The duration of the cycle, the recurrence interval between major earthquakes on a fault segment, varies from decades for rapidly loading faults to centuries or millennia for slowly loading faults. Estimating recurrence intervals is crucial for seismic hazard assessment, but remains challenging. Earthquake nucleation, the process initiating unstable rupture, is particularly mysterious. Faults experience continuous small stresses from tectonic loading, yet most of the time they don't rupture. What tips the balance from stability to instability? Proposed mechanisms include slow slip events increasing stress on locked fault patches, poor fluid pressure increases, reducing effective normal stress and friction, dynamic weakening mechanisms activating once slip begins, and cascading failure where initial small slips trigger larger ruptures. Slow slip events, or SSEs, are fault slip episodes lasting days to months at rates between continuous creep and earthquake slip rates. SSEs were discovered in the 2000s through GPS measurements showing gradual displacement not accompanied by seismic radiation. The Cascadia subduction zone offshore the Pacific Northwest experiences SSEs every approximately 14 months, each moving the overlying crust several centimeters over approximately 2 weeks. Some SSEs correlate with increased microseismicity or tremor, suggesting they might increase stress on adjacent locked fault sections, potentially triggering earthquakes. Episodic tremor and slip, or ETS episodes, combine slow slip with tectonic tremor, long-duration seismic signals distinct from typical earthquakes. Tremor appears to represent numerous small slip events occurring on the fault, possibly in fluid-rich regions, or on the deep extensions of faults transitioning from locked to continuously creeping behavior. The relationship between ETS episodes and major earthquakes remains unclear. Do they relieve stress, reducing earthquake likelihood, or do they increase stress on locked sections, increasing likelihood? Foreshocks, earthquakes preceding larger main shocks, occur before approximately 50% of major earthquakes, suggesting they might provide short-term warning. However, distinguishing foreshocks from background seismicity before the main shock occurs is extremely challenging. Only in retrospect can we identify that earlier events were foreshocks. Some main shocks have no foreshocks, while many small earthquakes that could be interpreted as foreshocks are not followed by larger events. Statistical approaches attempt to identify elevated seismicity rates that might indicate increased main shock probability, but practical earthquake prediction remains elusive. Aftershocks, earthquakes following main shocks, are better understood than foreshocks, following empirical laws including Amori's law describing how aftershock rate decays with time following the main shock. Aftershocks result from stress redistribution following the main shock, which increases stress on some fault sections while decreasing it on others. Regions where stress increased experience elevated seismicity for days to years after the main shock. The largest aftershock is typically approximately 1 magnitude smaller than the main shock, though occasionally an aftershock exceeds the initial event, in which case the nomenclature is revised. The relationship between fault geometry and earthquake behavior is complex. Simple planar faults might be expected to produce periodic earthquakes as stress accumulates and releases regularly, but observations reveal much more complex behavior. Fault roughness at multiple scales creates geometric barriers and asperities, strongly locked patches that affect rupture propagation. Stress heterogeneity from previous earthquake sequences influences where and how faults rupture. Fault intersections and stepovers, where faults offset or meet, can stop ruptures or allow them to continue depending on geometry and stress conditions. Earthquake magnitude scales quantify earthquake size. The Richter scale, developed in 1935, measured local earthquake magnitude based on peak ground motion amplitude. Modern magnitude scales, including moment magnitude MW, are based on the seismic moment, the product of fault area, average slip, and rock rigidity, which directly represents the energy released. Moment magnitude is approximately continuous and doesn't saturate for large earthquakes like older scales. The largest recorded earthquake was the 1960 Chile earthquake at magnitude 9.5, releasing energy equivalent to approximately 10,000 Hiroshima bombs. The Gutenberg-Richter relationship describes the frequency-magnitude distribution of earthquakes. The number of earthquakes increases exponentially as magnitude decreases. For every magnitude unit decrease, approximately 10 times more earthquakes occur. This power law distribution means small earthquakes vastly outnumber large ones. Millions of micro-earthquakes occur annually, while magnitude 9 earthquakes occur approximately once per decade globally. The power law distribution and its implications for seismic hazard assessment are well established, though the physical mechanisms producing this distribution remain debated. The maximum possible earthquake magnitude for a given fault depends on fault geometry and tectonic setting. Subduction zones, where oceanic plates descend beneath continental or other oceanic plates, can produce the largest earthquakes because they have enormous fault areas, potentially hundreds of kilometers long and 100 kilometers wide. The largest strike-slip faults, like the San Andreas, can produce approximately magnitude 7.8 to 8 earthquakes. Understanding maximum magnitudes is crucial for seismic hazard assessment and engineering design, but uncertainty is substantial, particularly for faults without historical major earthquakes. Induced seismicity, earthquakes triggered by human activities, has become increasingly recognized as a significant hazard. Reservoir-induced seismicity occurs when large dams impound water, increasing pore fluid pressure in underlying faults. The Koyna earthquake in India in 1967, killing approximately 200 people, followed reservoir filling. Injection-induced seismicity results from fluid injection for wastewater disposal, hydraulic fracturing, or geothermal energy, increasing pore pressure and reducing effective stress. The dramatic increase in Oklahoma seismicity from approximately 2 per year before 2008 to approximately 900 per year by 2015 followed increased wastewater injection from oil and gas operations. The fluid pressure's role in triggering earthquakes is well established. Increased pore pressure reduces effective normal stress on faults, reducing frictional strength and promoting slip. However, the details of how fluids migrate through rock, how quickly pressure diffuses, and how much pressure increase is needed to trigger rupture depend on rock permeability, fault zone structure, and stress state, all poorly constrained in most locations. Some induced earthquakes occur years after injection begins, and some occur kilometers from injection wells, indicating complex fluid migration paths and stress interactions. Earthquake early warning systems detect earthquakes immediately after they begin and send alerts to regions not yet experiencing shaking, potentially providing seconds to tens of seconds of warning before strong shaking arrives. The systems exploit the fact that seismic waves travel at finite speeds, a few kilometers per second, while electronic signals travel at light speed. For earthquakes 100 kilometers away, perhaps 20 to 30 seconds of warning might be available, enough to automatically halt trains, close gas valves, and allow people to take cover. Such systems operate in Japan, Mexico, and California, but their effectiveness depends on dense seismic networks and rapid automated processing. The ultimate goal of earthquake prediction, specifying the time, location, and magnitude of future earthquakes with useful precision, remains unrealized despite decades of effort. Proposed precursory phenomena including changes in groundwater levels, radon emissions, electromagnetic signals, and animal behavior have been investigated extensively, but none have proven reliably predictive. The challenge is that similar observations occur without being followed by earthquakes, creating false alarms, while many earthquakes occur without clear precursors. The low signal-to-noise ratio and the irregular, complex nature of earthquake processes make prediction extremely difficult, perhaps fundamentally impossible. The San Andreas Fault in California represents one of the world's most studied and monitored faults, yet prediction remains impossible. The fault accommodates approximately 34 millimeters per year of motion between the Pacific and North American plates through a combination of creep, continuous sliding on some segments, and locked behavior on others where stress accumulates between earthquakes. The southern segment near Los Angeles has not ruptured since approximately 1700, and the northern segment near San Francisco last ruptured in the 1906 earthquake, leading to concerns about overdue major earthquakes, though the concept of overdue is simplistic given the variability in recurrence intervals. The role of fault zone structure in earthquake behavior has become increasingly appreciated. Fault zones are not simple planar surfaces, but rather complex damage zones containing fractured rock, altered minerals, and sometimes significant amounts of fluids. The structure affects how faults slip, where ruptures nucleate and stop, and how stress transfers. High-velocity friction experiments simulating earthquake slip rates reveal dramatic weakening mechanisms, including flash heating at microscopic asperity contacts, thermal pressurization of pore fluids, and formation of molten or amorphous materials, all of which could allow earthquake ruptures to propagate despite high sliding velocities. The earthquake rupture process itself involves propagation of the rupture front along the fault at speeds approaching but not exceeding the shear wave speed, typically a few kilometers per second. The rupture front is the boundary separating slipped from unslipped portions of the fault. Ahead of this front, stress concentrations build as the fault is loaded by the approaching rupture. Behind the front, the fault slips, radiating seismic waves. The details of rupture propagation, including whether ruptures accelerate or decelerate, whether they jump across gaps, and where they stop depend on fault properties, stress conditions, and dynamic processes poorly constrained by observations. Supershear earthquakes represent a special class where rupture velocities exceed the shear wave speed, approaching the faster P-wave speed. These earthquakes produce distinctive seismic radiation patterns and potentially more intense ground shaking. They require special conditions, including high pre-stress and favorable fault geometry. The 2002 Denali earthquake in Alaska included a supershear rupture segment, and observations from this and other events provide insights into the conditions allowing supershear propagation. Tsunami generation by earthquakes depends on seafloor displacement. Vertical motion of the ocean floor during submarine earthquakes displaces water, creating waves that propagate across oceans. Not all submarine earthquakes generate significant tsunamis. Those with large vertical displacements or occurring in shallow water are most tsunami-genic. The 2004 Sumatra earthquake generated a devastating tsunami that killed over 230,000 people across the Indian Ocean. Understanding which earthquakes will generate tsunamis and how quickly waves will arrive at coastlines is crucial for warning systems. Deep ocean trenches contain ecosystems thriving in extreme conditions, but the full biodiversity and ecology remain poorly known. The deepest parts of the ocean, the Hadal Zone below 6,000 meters depth, represent one of Earth's most extreme and least explored environments. Occurring primarily in oceanic trenches where tectonic plates subduct, these depths experience crushing pressures exceeding 1,000 atmospheres, near freezing temperatures, complete darkness, and limited food supply, yet support diverse ecosystems adapted to these extreme conditions. The biology, geology, and chemistry of Hadal zones remain incompletely characterized despite their significance for understanding life's limits. The Mariana Trench in the western Pacific contains the deepest known point, Challenger Deep, reaching approximately 10,920 meters below sea level. At this depth, pressure exceeds 1,090 atmospheres, over 16,000 pounds per square inch, which would instantly crush most human-made equipment and organisms not adapted to such conditions. The trench formed where the Pacific Plate subducts beneath the Mariana Plate, creating a narrow depression averaging 69 kilometers wide and extending approximately 2,550 kilometers in length. Other major trenches include the Tonga Trench, reaching approximately 10,880 meters, the Philippine Trench at approximately 10,540 meters, and the Kermadec and Kuril-Kamchatka trenches exceeding 10,000 meters. These trenches collectively comprise a small fraction of ocean area, but represent the most extreme habitats on Earth's surface. Their exploration has been limited by the technical challenges of reaching such depths. Only 4 manned descents have reached Challenger Deep. In 1960, 2012, 2019 twice. The pressure at Hadal depths creates fundamental challenges for life. Biological molecules, including proteins and membranes, respond to pressure, with high pressure potentially disrupting protein folding, membrane fluidity, and enzyme function. Hadal organisms have evolved adaptations including pressure-adapted proteins with altered amino acid compositions, membranes enriched in unsaturated fatty acids maintaining fluidity under pressure, and cellular solutes including trimethylamine N-oxide or TMAO that stabilize proteins against pressure effects. These adaptations allow fish, crustaceans, worms, and microorganisms to thrive at depths where unprotected organisms would perish. Hadal fish include snailfish of the family Leporidae, which hold the depth record for fish at approximately 8,178 meters in the Mariana Trench. Below approximately 8,200 meters, no fish have been observed, suggesting a physiological depth limit possibly related to osmotic regulation challenges or protein stability at extreme pressure. Snailfish at great depths are small, gelatinous, and translucent, adapted to the food-limited environment. They lack swim bladders, gas-filled organs that would collapse under pressure, and have minimal skeletal ossification. Amphipods, small crustaceans related to shrimp, are abundant in Hadal trenches, with some species exceeding 20 centimeters in length, much larger than shallow-water amphipods. The amphipod Hyrndaleia gigas inhabits trenches worldwide at depths exceeding 10,000 meters. These scavengers rapidly locate and consume food falls, dead organisms sinking from above, representing a crucial pathway transferring organic matter from surface waters to hadal depths. Baited camera systems deployed in trenches attract swarms of amphipods within hours, demonstrating their efficiency at detecting and exploiting rare food sources. Microbial communities at hadal depths include bacteria and archaea adapted to high pressure, low temperature, and oligotrophic conditions. Some are barophiles or pisophiles, organisms requiring high pressure for optimal growth, rather than merely pressure tolerant. These microbes break down organic matter in sediments, remineralizing nutrients and supporting the food web. The diversity of hadal microbial communities and their metabolic capabilities remain incompletely characterized, with each new expedition discovering novel lineages and metabolic pathways. The food supply to hadal trenches comes primarily from sinking organic matter, marine snow composed of dead plankton, fecal pellets, and other detritus that settles from surface waters thousands of meters above. This flux is limited compared to shallower depths because most organic matter is consumed or remineralized before reaching hadal depths. Occasionally, large food falls, including dead whales or wood logs, sink to trench floors, supporting specialized communities that consume these bonanzas over months to years. Chemosynthetic communities based on chemical energy rather than sunlight have been proposed for hadal trenches, but remain poorly documented compared to hydrothermal vent communities at shallower depths. Subducting oceanic crust carries sediments rich in organic carbon into trenches, and microbial communities might exploit this carbon or chemical gradients associated with fluid flow from the subducting slab. However, the extent of chemosynthetic primary production in trenches remains uncertain. The role of trenches in global biogeochemical cycles is not fully understood. Subduction carries sediments, organic carbon, and water into Earth's interior, affecting the long-term carbon cycle and volatile recycling between surface and interior. Trenches are sites of intense physical and chemical gradients where sediment accumulation, diagenesis, chemical changes in sediments, and ultimately metamorphism and melting transform materials. Understanding these processes requires samples from hadal depths, which are difficult to obtain. The seismic activity associated with subduction zones affects hadal ecosystems through earthquakes and tsunamis. Major earthquakes can trigger underwater landslides depositing fresh sediment in trenches, potentially smothering benthic communities while providing fresh organic matter. Shaking might enhance fluid flow through sediments, creating chemical gradients supporting chemosynthetic communities. The 2011 Tohoku earthquake off Japan, which generated the devastating tsunami, affected the Japan trench ecosystem, though the biological impacts remain incompletely documented. Pollution has reached even the deepest ocean trenches. Anthropogenic chemicals, including persistent organic pollutants like PCBs and flame retardants, have been detected in hadal amphipods and fish. Microplastics occur in trench sediments. These findings demonstrate that human impacts extend to Earth's most remote environments, likely transported by sinking particles and accumulating in organisms at the base of the food web. The long-term ecosystem effects remain unknown. The exploration of hadal zones has been limited by technological challenges. Submersibles capable of reaching full ocean depth require specialized materials resisting extreme pressure, including titanium alloy pressure hulls and syntactic foam for buoyancy. Unmanned landers equipped with cameras, sensors, and sampling equipment provide cost-effective alternatives, dropped to the seafloor to collect data and samples before releasing ballast and surfacing. Hybrid remotely operated vehicles, or HROVs, tethered to surface ships through ultra-long cables allow real-time control, but face technical challenges at hadal depths. The discovery rate of new species in hadal zones is high, with most collected organisms representing undescribed species. Many hadal species show endemism, occurring in single trenches or small geographic ranges, suggesting limited dispersal between trenches despite the continuous nature of deep ocean waters. The physical separation of trenches by abyssal plains and mid-ocean ridges may restrict organism movement, promoting speciation. However, some species occur in multiple trenches separated by thousands of kilometers, indicating occasional dispersal. Comparative studies across multiple trenches are revealing biogeographic patterns. Trenches in the Pacific Ocean show higher diversity than trenches in other oceans, consistent with general deep-sea diversity patterns. Environmental factors including depth, food availability, and sediment characteristics influence community composition. Historical factors including trench age and isolation also play roles. Building a comprehensive understanding of hadal biogeography requires systematic sampling across trenches worldwide, an ongoing effort. The potential for hadal zones to inform astrobiology is significant. The extreme conditions, high pressure, low temperature, darkness, limited nutrients, resemble conditions hypothesized for subsurface oceans on moons including Europa, Enceladus, and Titan. Understanding how life adapts to hadal environments provides insights into what life might be like in extraterrestrial oceans. The molecular adaptations allowing proteins and membranes to function under pressure might represent solutions that evolved independently in alien biospheres. The hadal ecosystem structure differs fundamentally from shallow ecosystems. In shallow waters, photosynthesis by phytoplankton forms the base of food webs, supporting herbivorous zooplankton and fish that are consumed by higher predators. In hadal zones, the base consists of sinking organic detritus and occasional large food falls. The fauna is dominated by scavengers and deposit feeders rather than herbivores and active predators. The absence of primary production and the extreme conditions create simpler food webs with fewer trophic levels. The xenophyophores, giant single-celled organisms reaching sizes exceeding 10 centimeters, are among the most enigmatic hadal inhabitants. These protists construct delicate tests, shells, from sediment particles cemented together, creating structures visible to the naked eye despite being single cells. Their ecological role remains poorly understood, but they may be important in sediment processing and providing habitat structure for smaller organisms. Their presence at extreme depths, where other large organisms are rare, demonstrates the remarkable diversity of life forms adapted to hadal conditions. The origin of life on Earth approximately 3.8 billion years ago represents one of the deepest unsolved mysteries. The transition from chemistry to biology, from non-living molecules to self-replicating, evolving organisms, represents one of science's most profound unsolved questions. While laboratory experiments have demonstrated that complex organic molecules, including amino acids and nucleotide precursors, can form under plausible early Earth conditions, the pathway from these building blocks to living cells remains largely mysterious, with competing hypotheses about the location, timing, and chemical mechanisms involved. The early Earth environment differed dramatically from the present, creating both challenges and opportunities for life's origin. The atmosphere was likely dominated by nitrogen and carbon dioxide, with smaller amounts of methane, hydrogen, and other gases, but lacking the free oxygen that characterizes the modern atmosphere. Oxygen only accumulated after photosynthetic organisms evolved, approximately 2.4 billion years ago during the Great Oxidation Event. The oxygen-poor atmosphere would have lacked an ozone layer, allowing intense ultraviolet radiation to reach the surface. The surface temperature of early Earth remains debated. Some models suggest Earth experienced a faint young sun problem. The sun's luminosity was approximately 25 to 30% lower than present, potentially causing widespread glaciation without compensating greenhouse warming. Proposed solutions include higher atmospheric carbon dioxide concentrations from volcanic outgassing, methane from methanogenic microbes, or other greenhouse gases. Alternatively, early Earth may have been warm due to residual heat from formation, tidal heating from a closer moon, or impacts from the late heavy bombardment. The source of organic molecules for life's origin could have included synthesis on Earth, delivery from space, or both. The Miller-Urey experiment in 1953 demonstrated that amino acids could form from spark discharges, simulating lightning, in reducing atmospheres containing methane, ammonia, and hydrogen. However, the early atmosphere was probably less reducing than Miller and Urey assumed, reducing the efficiency of such synthesis. Alternative energy sources, including ultraviolet radiation, shock waves from meteorite impacts, and hydrothermal systems, could have driven organic synthesis. Delivery of organic molecules from space through meteorites and comets likely contributed substantially to Earth's organic inventory. Carbonaceous chondrite meteorites contain diverse organic molecules, including amino acids, nucleotide bases, and sugars formed through abiotic processes in space. The heavy bombardment of early Earth by asteroids and comets would have delivered enormous quantities of organic molecules, though high-energy impacts would also have destroyed some organics. The balance between delivery and destruction depends on impact velocities and atmospheric properties. The location of life's origin is uncertain, with proposed environments including Darwin's warm little pond, deep-sea hydrothermal vents, shallow submarine hot springs, and surface pools on volcanic islands. Each environment offers different advantages and faces different challenges. Surface pools receive sunlight for photochemistry and experience wet-dry cycles that could concentrate molecules, but face destruction from UV radiation and impacts. Hydrothermal vents provide chemical energy from redox gradients and protection from impacts, but face challenges from extreme temperatures and dilution in the ocean. Alkaline hydrothermal vents, which emit moderate temperature fluids rich in hydrogen, have gained support as possible sites for life's origin. These vents create natural electrochemical gradients across thin mineral barriers, separating alkaline vent fluids from acidic ocean water, gradients resembling those used by all life for energy metabolism. The hypothesis proposes that life originated within microscopic pores in vent structures, with the mineral barriers serving as primitive membranes before biological membranes evolved. The RNA world hypothesis proposes that early life used RNA for both genetic information storage and catalytic functions, before DNA and proteins evolved. This hypothesis is motivated by RNA's dual capabilities. It can store information through its nucleotide sequence and catalyze reactions through its tertiary structure. as demonstrated by the discovery of ribozymes. Modern cells use RNA in crucial roles, including ribosomal RNA, catalyzing protein synthesis, suggesting RNA's ancient centrality to life. However, the RNA world faces significant challenges. Synthesizing RNA nucleotides from simple precursors under plausible prebiotic conditions is difficult. Ribose, the sugar component of RNA, is unstable and difficult to synthesize selectively. Linking ribose with phosphate and nucleotide bases requires specific conditions. Polymerizing nucleotides into RNA without enzymes is inefficient. These challenges have led some researchers to propose that simpler genetic molecules preceded RNA, with candidates including peptide nucleic acid or threose nucleic acid. The emergence of cellular compartments, membranes separating protocells from their environment, was crucial for life's origin. Amphiphilic molecules with hydrophobic and hydrophilic regions spontaneously form vesicles in water, creating primitive compartments. Fatty acids, which could have been abundant on early Earth, form vesicles that can grow, divide, and encapsulate molecules. The transition from simple fatty acid vesicles to complex phospholipid membranes with embedded proteins represents a major evolutionary innovation poorly understood from available evidence. The metabolism-first hypothesis proposes that self-sustaining chemical reaction networks preceded genetic molecules, with autocatalytic cycles producing their own catalysts. In this view, life began with chemical networks that could harvest energy from the environment and produce complex molecules, with genetic information storage evolving later to stabilize and optimize successful networks. The citric acid cycle, central to modern metabolism, has been proposed as a possible prebiotic cycle because some of its reactions can occur without enzymes under certain conditions. The genetic code, the mapping between nucleotide triplets and amino acids, appears nearly universal across life, suggesting it was established before the last universal common ancestor, or LUCA. The code structure is non-random, with chemically similar amino acids often encoded by similar codons, suggesting that the code evolved to minimize errors from mutations. How this sophisticated code emerged from simpler precursors remains mysterious, though hypotheses propose gradual expansion from simpler codes involving fewer amino acids. The timing of life's origin is constrained by multiple lines of evidence. The oldest claimed evidence for life comes from rocks in Greenland dated to approximately 3.8 billion years ago, with carbon isotope ratios interpreted as biological signatures, though these claims are controversial. Less controversial evidence from approximately 3.5 billion years ago includes stromatolites, layered structures built by microbial mats, and microfossils resembling bacteria. These findings suggest life originated before 3.8 billion years ago, possibly within a few hundred million years after Earth became habitable. The rapid origin of life on Earth, within perhaps 500 million years after the planet cooled enough for liquid water, has been interpreted by some as suggesting that life arises readily when conditions permit. However, alternative interpretations exist. Perhaps we're missing key constraints and suitable conditions existed earlier, or perhaps life originated multiple times with earlier origins being destroyed by impacts, or perhaps Earth was fortunate and life's origin is actually quite rare. Distinguishing these possibilities requires finding life elsewhere or understanding life's origin mechanism in detail. The protocell hypothesis proposes that life originated as simple vesicles containing self-replicating molecules and primitive metabolism. The integration of these components, membranes, genetics, and metabolism, represents a major challenge for origin scenarios. Each component is complex, and their coordination even more so. How did these systems become coupled such that membrane composition affected enclosed chemistry, genetic molecules influenced metabolism, and metabolic products supported membrane synthesis and genetic replication? The role of minerals and surfaces in life's origin has received increasing attention. Clays can concentrate organic molecules, catalyze polymerization, and provide structural support. Iron-sulfur minerals common at hydrothermal vents catalyze reduction reactions central to many metabolic pathways. The transition from mineral-catalyzed chemistry to enzyme-catalyzed biochemistry may have been gradual, with organic molecules initially assisting mineral catalysts before replacing them entirely. The chirality problem, the fact that life uses exclusively left-handed amino acids and right-handed sugars, remains unexplained. Abiotic synthesis produces equal mixtures of left and right-handed forms, so something must have broken this symmetry. Proposed mechanisms include circularly polarized UV light favoring one-handedness, autocatalytic processes amplifying small initial asymmetries, or chance, one-handedness randomly dominated initially and subsequent evolution maintained it. Evidence for which mechanism operated is lacking. The philosophical implications of life's origin extend beyond the scientific questions. Understanding how life arose from chemistry informs debates about the prevalence of life in the universe, the relationship between matter and information, and the boundaries between living and non-living systems. Some researchers propose that life is an expected outcome of thermodynamic principles driving systems to dissipate energy gradients more efficiently. Others emphasize the role of contingency and chance in the specific pathway that led to Earth's biology. Mass extinctions occurred at irregular intervals throughout Earth's history, and the causes of some remain controversial. The extinction of species represents a normal component of evolution, with background extinction rates seeing species disappear and be replaced continuously. However, the geological record reveals 5 major mass extinctions, where large fractions of species disappeared within geologically brief intervals, along with numerous smaller extinction events. While some mass extinctions have well-established causes, others remain incompletely explained, and the possibility of common trigger mechanisms or periodic patterns continues to generate research and debate. The 5 major mass extinctions are the Ordovician Silurian approximately 445 million years ago, Late Devonian approximately 375 million years ago, Permian-Triassic approximately 252 million years ago, Triassic-Jurassic approximately 200 million years ago, and Cretaceous-Paleogene approximately 66 million years ago. Each eliminated substantial fractions of marine and terrestrial species, reshaped ecosystems, and influenced subsequent evolution. The severity ranges from approximately 70% species loss in the Ordovician event to approximately 95% in the Permian event, the most severe known extinction. The Permian-Triassic extinction, also called the Great Dying, represents Earth's most severe biodiversity crisis. Marine ecosystems were decimated, with trilobites, rugose corals, many brachiopods, and other groups going extinct. Terrestrial ecosystems also suffered severe losses. The extinction's cause is attributed to massive volcanism in the Siberian traps, where flood basalts covered millions of square kilometers and released enormous quantities of carbon dioxide, sulfur dioxide, and other gases. The resulting greenhouse warming, ocean acidification, and anoxia created lethal conditions lasting hundreds of thousands of years. The Cretaceous-Paleogene extinction, which killed the non-avian dinosaurs, is attributed to the Chicxulub asteroid impact in Mexico, combined with volcanism in the Deccan Traps in India. The impact created global devastation through ejecta, wildfires, darkness from atmospheric dust, and subsequent cooling. The Deccan volcanism released gases, causing acidification and warming on longer timescales. The relative contributions of impact versus volcanism are debated, with some researchers emphasizing the impact's role and others suggesting volcanism was equally important. The late Devonian extinction actually consisted of multiple pulses over approximately 20 million years, killing approximately 75% of species. The causes remain uncertain, with proposed mechanisms including anoxia in shallow marine environments, cooling events, sea level changes, and possibly bolide impacts. Evidence for impacts includes spheral layers and iridium anomalies at some extinction boundaries, but the evidence is not as clear as for the KPG impact. Multiple factors may have contributed to the protracted extinction interval. The search for periodicity in mass extinctions has generated controversy. Analysis of extinction rates over the past 260 million years suggested a 26 million year cycle, leading to hypotheses about astronomical forcing mechanisms. Proposed causes for periodic extinctions include comet showers from Oort cloud disturbances by a hypothetical companion star to the Sun called Nemesis, or by the solar system's passage through the galactic plane. However, the statistical evidence for periodicity is debated, and searches for Nemesis have been unsuccessful. The role of volcanism in mass extinctions extends beyond direct effects of eruptions. Large igneous provinces or lips, episodes of flood basalt volcanism producing millions of cubic kilometers of basalt, correlate temporally with several major extinctions. The volcanic emissions include carbon dioxide causing greenhouse warming, sulfur dioxide causing short-term cooling, and halogens destroying ozone. The eruptions can trigger additional feedbacks, including release of methane from warming ocean sediments and disruption of ocean circulation. Ocean anoxia, depletion of dissolved oxygen, appears to have played a role in multiple mass extinctions. Anoxia can result from warming reducing oxygen solubility, nutrient inputs stimulating productivity that consumes oxygen during decomposition, or circulation changes, reducing oxygen delivery to deep waters. Anoxic events are recorded in black shales deposited in oxygen-depleted waters rich in organic matter. The extent of anoxia during different extinctions and its relative importance compared to other kill mechanisms remain active research areas. The relationship between climate change and mass extinctions is complex. Rapid warming or cooling can stress ecosystems, but the rate of change may be as important as the magnitude. Some mass extinctions are associated with cooling and glaciation, including the Ordovician-Silurian event linked to the late Ordovician glaciation. Others are associated with warming, including the Permian Triassic associated with extreme greenhouse conditions. The mechanisms linking temperature changes to extinction vary and may include habitat loss, disrupted food webs, and exceeding physiological tolerances. Smaller extinction events punctuate the record between major mass extinctions. The Paleocene thermal maximum, approximately 56 million years ago, saw rapid warming and ocean acidification, causing extinctions primarily in deep-sea benthic foraminifera. The Toarcian extinction, approximately 183 million years ago, eliminated approximately 30 to 40% of species, and is associated with ocean anoxia and carbon cycle perturbations. These smaller events provide additional tests of extinction mechanisms and warnings about rapid environmental change. The current biodiversity crisis, driven by human activities, is sometimes called the sixth mass extinction. Extinction rates are elevated by 1 to 3 orders of magnitude above background rates, with habitat destruction, invasive species, overexploitation, pollution, and climate change driving losses. Whether this qualifies as a mass extinction depends on definitions and timeframes. If current trends continue for centuries, extinction magnitudes could reach mass extinction levels. However, the compressed timeframe and direct human agency distinguish this event from previous extinctions. The recovery from mass extinctions typically takes millions of years, with ecosystems reorganizing in ways that can differ substantially from pre-extinction configurations. The extinction of dominant groups creates ecological opportunities for survivors to diversify and adapt to vacant niches. The Cretaceous-Paleogene extinction eliminated dinosaurs, allowing mammals to radiate into diverse terrestrial niches. The Permian-Triassic extinction eliminated many Paleozoic groups, allowing modern groups including dinosaurs and mammals to eventually rise to prominence. Lazarus taxa, groups that disappear from the fossil record during extinctions but reappear later, complicate extinction studies. These taxa apparently survived in refugia or low abundances that escaped fossilization, creating gaps in the record. Distinguishing true extinctions from Lazarus absences requires careful sampling and statistical analysis. Some claimed extinctions may represent local disappearances or preservation failures rather than global elimination. The selectivity of extinctions, which groups suffered most severely, provides insights into kill mechanisms. If extinction results from habitat loss, groups with narrow habitat requirements suffer more than generalists. If extinction results from food web collapse, groups at high trophic levels, or depending on specific food sources, suffer disproportionately. If extinction results from environmental extremes, groups with narrow physiological tolerances suffer more than tolerant groups. Analyzing selectivity patterns helps discriminate among proposed mechanisms. Strange gravitational anomalies and variations in Earth's rotation reveal complex interior structures and dynamics. Precise measurements of Earth's gravitational field reveal that it is not uniform, but varies slightly from place to place due to variations in the distribution of mass within Earth. These variations, measured by satellites and gravimeters, provide information about Earth's interior structure, tectonic processes, and even climate-related mass redistributions. Some gravitational anomalies remain incompletely explained, representing mysteries about Earth's internal structure and dynamics. Earth's gravitational field is dominated by a uniform component proportional to Earth's total mass, but deviations from uniformity, called gravity anomalies, reveal density variations. Positive anomalies occur where mass concentrations or masscons exist, regions denser than surroundings, while negative anomalies occur where mass deficits exist. Satellite missions, including GRACE and its successor GRACE-FO, measure the gravity field with unprecedented precision, detecting variations smaller than 1 part in 10 million. The geoid, the surface where gravitational potential is constant, approximated by mean sea level, is not a perfect sphere, but has bumps and depressions reflecting mass distribution. The geoid depression near India, where the surface is approximately 100 meters lower than a perfect sphere would be, represents a major anomaly. Proposed explanations include lower than average density in the underlying mantle, possibly related to subducted slabs or mantle convection patterns, but the exact cause remains debated. Variations in Earth's rotation rate occur on timescales from days to millennia, reflecting mass redistribution and angular momentum exchange among Earth's components. Seasonal variations result from atmospheric mass redistribution and water storage changes. Decadal variations correlate with core mantle coupling and possibly inner core dynamics. Tidal friction from the Moon causes long-term slowing of Earth's rotation, lengthening the day by approximately 2 milliseconds per century. These variations are measured with microsecond precision by atomic clocks and satellite observations. The Chandler wobble, a small variation in the position of Earth's rotation axis relative to the surface, has a period of approximately 14 months and amplitude of several meters. This wobble represents free oscillation of Earth's rotation axis, similar to how a spinning top wobbles. The excitation mechanism maintaining the wobble against damping is not fully understood, though candidates include atmospheric pressure variations, ocean currents, and core mantle coupling. Recent observations suggest the wobble's amplitude varies over decades, adding additional mystery. Precession of the equinoxes, the slow change in the direction Earth's rotation axis points, occurs on a 26,000-year cycle due to gravitational torques from the Sun and Moon acting on Earth's equatorial bulge. This precession causes the positions of stars to shift slowly over millennia and determines which star is the North Star at different epochs. Variations in precession rate can result from changes in Earth's moment of inertia due to ice sheet growth and melting, post-glacial rebound, or core mantle interactions. The free core nutation, an oscillation of Earth's rotation axis with a period of approximately 430 days, results from coupling between the mantle and the liquid outer core. The phenomenon reveals that the core is not rigidly coupled to the mantle, but can rotate slightly differently, affecting Earth's overall rotation. Precise measurements of this nutation provide constraints on core properties, including its ellipticity and density distribution. Post-glacial rebound or glacial isostatic adjustment continues affecting Earth's shape and gravitational field thousands of years after ice sheets melted. Regions that were ice-covered during glacial maxima, including Scandinavia and Canada, continue rising as the mantle flows back into regions from which it was displaced by ice weight. This ongoing adjustment causes measurable changes in both surface height and gravitational field that must be accounted for when interpreting gravity measurements for other purposes. The degree 2 harmonics of the gravity field, the quadrupole components describing Earth's overall shape, are particularly sensitive to mass redistribution in the mantle and core. Precise measurements of these harmonics constrain models of mantle convection and core dynamics. Changes in degree 2 harmonics over time reveal ongoing mantle convection and possibly core processes, though separating signals from different sources is challenging. Present-day mass redistribution from climate change is detectable in gravity measurements. Ice mass loss from Greenland and Antarctica changes the gravitational field, with negative anomalies developing over regions losing ice mass. GRACE satellites detected this signal clearly, demonstrating both the ice loss and the utility of satellite gravimetry for monitoring climate change. Groundwater depletion in aquifers also creates detectable gravity changes, allowing monitoring of water resources from space. The Love numbers, parameters describing Earth's deformation in response to tidal forces, provide information about interior structure and rheology. The solid Earth deforms elastically in response to tidal forces from the Moon and Sun, with the magnitude of deformation depending on internal structure and composition. Measurements of tidal deformation through satellite altimetry and gravimetry constrain mantle viscosity profiles and core mantle boundary properties. The existence of lateral variations in mantle structure, seismic tomography reveals slow and fast regions, creates density variations that affect the gravity field. Subducted slabs, being colder and denser than surrounding mantle, create positive gravity anomalies. Mantle plumes, being hotter and less dense, create negative anomalies. Mapping these anomalies helps constrain mantle convection patterns and the fate of subducted material, though converting seismic velocity anomalies to density anomalies involves assumptions about composition and mineralogy. The core mantle boundary at approximately 2,900 kilometers depth separates the silicate mantle from the liquid iron core, representing one of Earth's most important discontinuities. Topography on this boundary, variations in depth, affects the gravitational field and mantle convection. The boundary is not smooth, but has relief of several kilometers associated with mantle plumes, subducted slab remnants, and large low-shear velocity provinces. Understanding this topography is crucial for modeling mantle-core interactions. If you're still awake somewhere in this exploration of Earth's mysteries, of magnetic reversals and moon origins, of ice ages and inner core rotation, of earthquakes and deep trenches, of life's origins and mass extinctions, of gravitational anomalies and rotation variations, there's more to discover about the unsolved puzzles of our planet. But if sleep has found you, if consciousness has faded into dreams, then rest knowing that beneath your feet and far above you, Earth continues its patient work of shifting, cycling, and changing in ways we're only beginning to understand. While you sleep tonight, the Earth beneath you is in constant motion. Tectonic plates are creeping across the asthenosphere at rates of centimeters per year, slower than fingernail growth, but inexorable over geologic time. The Pacific Plate is sliding northwest under Japan and the Philippines, storing elastic strain that will eventually release in earthquakes. The Nazca Plate is subducting beneath South America, feeding magma to Andean volcanoes. The African Plate is slowly splitting along the East African Rift, eventually creating a new ocean basin over millions of years. The magnetic field generated thousands of kilometers below the surface extends into space, deflecting solar wind particles and protecting the atmosphere from erosion. The field's strength and configuration vary over timescales from days, magnetic storms from solar events, to millions of years, reversals and excursions. Whether the current decline in field strength presages an impending reversal or simply represents normal fluctuation remains unknown. The dynamo process generating the field operates continuously, with complex flow patterns in the outer core creating the field geometry through mechanisms we simulate but don't fully understand. The moon above you, if visible tonight, is slowly receding from Earth at approximately 3.8 centimeters per year, a consequence of tidal friction transferring angular momentum from Earth's rotation to the Moon's orbit. When dinosaurs walked the Earth, the Moon was closer and days were shorter, approximately 23 hours rather than 24. In the distant future, the Moon will recede until the length of Earth's day equals the length of the lunar month, approximately 47 current days, and the Moon will appear stationary over one point on Earth, though this equilibrium is billions of years away. Earth's climate system continues cycling energy, water, and carbon through reservoirs including the atmosphere, ocean, cryosphere, and biosphere. Whether the current state represents a transient in an orbital cycle that will eventually return to glacial conditions, or whether human greenhouse gas emissions have fundamentally altered the climate trajectory, engaging a super-interglacial that disrupts the Milankovitch cycles remains an active question. The climate sensitivity to both orbital variations and greenhouse gas concentrations creates complex dynamics where multiple forcings interact. Deep beneath your sleeping location, the inner core continues its mysterious rotation or oscillation. Driven by electromagnetic and gravitational forces we can infer but not directly observe. Whether it's currently rotating faster, slower, or at the same rate as the surface, and whether its rotation rate varies on decadal timescales, depends on which research studies you believe, a scientific controversy still unresolved. The seismic waves from earthquakes traveling through the inner core and recorded at seismometers worldwide continue providing data that researchers analyze using different methods and interpret differently. In the Hadal Trenches kilometers deep in the ocean, amphipods are scavenging the seafloor, searching for the rare food falls that sustain Hadal ecosystems. Snailfish are hunting smaller prey in complete darkness at pressures that would crush unprotected organisms instantly. Microbes in trench sediments are breaking down organic matter, recycling nutrients through pathways that remain largely uncharacterized. The subduction occurring beneath trenches is carrying water, sediment, and carbon into Earth's interior, participating in global cycles operating over millions of years. The Earth's surface and interior are not static, but dynamic systems operating across timescales from seconds, earthquake ruptures, to billions of years, planetary evolution. Many processes remain incompletely understood because they operate on timescales exceeding human observation, because they occur in inaccessible locations, or because they involve complex interactions among multiple systems. Understanding Earth requires integrating observations, experiments, and models while acknowledging the substantial uncertainties and unknowns that remain. Consider the fact that beneath the familiar surface where we live, Earth's interior extends 6,370 kilometers to the center, consisting of layers we've never directly sampled. Everything we know about the core comes from indirect observations, seismic waves, magnetic field measurements, geodesy, and laboratory experiments on materials under extreme pressure and temperature. The properties, composition, and dynamics of the core remain constrained but not precisely known, with debates continuing about iron phase, light element content, thermal structure, and flow patterns. The scientific method allows incremental progress on Earth mysteries through hypothesis formulation, prediction, observation, and refinement. Early hypotheses about continental drift were rejected for lack of mechanism, but later vindicated by seafloor spreading observations. Early proposals that orbital variations drive ice ages were dismissed as too weak, but later confirmed through improved understanding of feedbacks. Early suggestions that the inner core rotates independently generated skepticism, but initiated research programs that continue refining understanding even if consensus remains elusive. Some Earth mysteries might be fundamentally unsolvable with current or foreseeable methods. Predicting specific earthquakes might be impossible because of deterministic chaos, high sensitivity to initial conditions making long-term prediction impossible even if the underlying physics is deterministic. The unique history of planetary formation might mean that we cannot fully test moon formation hypotheses because we cannot rerun the experiment or observe similar events elsewhere with sufficient detail. The stochastic nature of some processes might mean we can describe statistical behavior without predicting individual events. Yet other mysteries that seemed intractable have yielded to new observations or methods. Plate tectonics revolutionized Earth science despite seeming impossible to earlier generations who couldn't imagine continents moving. The discovery of the inner core from seismic wave analysis revealed structure invisible to direct observation. The recovery of ice cores, sampling 800,000 years of climate history, provided unprecedented paleoclimate records. Future advances in instrumentation, computation, or theory may similarly resolve current mysteries. The exploration of Earth continues through multiple approaches. Seismic networks monitor earthquakes while also illuminating interior structure through seismic tomography. Ocean drilling recovers sediment cores, preserving climate history, and samples oceanic crust. Satellite measurements track surface deformation, gravity variations, and magnetic field changes with increasing precision. Laboratory experiments subject rocks and minerals to core conditions. Computer simulations model processes spanning from microscopic crystal dynamics to global mantle convection. Each approach contributes pieces to the larger puzzle. Consider, as you drift towards sleep or have already fallen, that the planet beneath you has existed for 4.54 billion years, harboring mysteries that span from its violent formation through collisions and differentiation, through the emergence of life and its influence on the atmosphere and surface, through cycles of supercontinent formation and breakup, through climate extremes from snowball Earth episodes to hothouse periods, to the present when one species has developed technology to study planetary history and processes. The Earth beneath and around you is both familiar and mysterious. We understand the basic processes, plate tectonics, the water cycle, the carbon cycle, orbital variations, but mysteries remain in the details, the triggers, the feedbacks, and the interactions. Science progresses by identifying what we don't know, formulating hypotheses, and testing them. The mysteries remaining today represent opportunities for tomorrow's discoveries, questions for future generations to investigate using tools and techniques not yet invented. The story of Earth is written in rocks, ice, sediments, and the structures deep below. Each layer, each mineral, each isotopic signature contains information about past conditions, processes, and events. Reading this story requires techniques spanning multiple disciplines: geology, geophysics, geochemistry, biology, physics, and mathematics. The interdisciplinary nature of Earth science reflects the interconnectedness of Earth systems, where changes in one realm affect others through complex feedbacks and couplings. Your very existence connects to these Earth mysteries in profound ways. The elements in your body were created in stars and delivered to Earth during its formation. The oxygen you breathe was produced by photosynthetic organisms that evolved on early Earth. The stable climate that allowed human civilization to develop reflects orbital configurations, ocean circulation patterns, and atmospheric composition. The magnetic field shielding Earth from radiation enabled life to thrive on the surface rather than being confined to protected environments. The future holds new mysteries as Earth continues evolving. How will the magnetic field behave over coming centuries? When will the next major earthquake strike vulnerable regions? How will climate respond to continued greenhouse gas emissions? Will we discover life in Earth's deep biosphere or in subsurface oceans of icy moons? Each answered question raises new ones, ensuring that Earth science will continue offering puzzles for generations to come. See you next time.